Hello friends, today I'm back with another way of exploiting a direct return exploit. This method is basically useful for exploiting in scenarios where you have a direct return that you control. So in this case you are able to control the EIP directly, however you don't have enough space, and as a result of that you cannot put the shellcode after the ESP jump. Now, normally in case of Linux exploits, what you usually do is, um, if that is the case, you hardcode the value of your ESP, or rather than saying hardcode the value of some pointer on the stack where your shellcode resides, and that way you can bypass that. However, in case of Windows, um, as Linux is much more stable, it seems Windows isn't, so it might remain stable for the time being when you try to exploit it and hardcode the value. However, the same exploit probably will not work on another system. So on Windows, basically an easier way is to use values such as jump EAX or jump ESP, call ESP. So pointers to those instructions from one of the DLLs. That is much more reliable rather than hard coding the value of a stack pointer on the stack. This has nothing to do with respect to the ASLR aspect. In Windows, it seems, since the DLLs keep on changing and the way the load addresses change every now and then, that is usually the reason that anything before Vista, where ASLR was not enabled, uh, would have the problem of not being able to hardcode the value. So usually in a direct return exploit, what you end up doing is overflow the stack followed by the return pointer, which is usually jump ESP or call ESP, or some kind of register that is pointing to your shellcode string. However, in my case, this was a specific scenario where the exploit required me to use the the payload to be placed basically before the jump pointer, because if I ended up using more space than the exploit would not work. So in this case, basically what I have to do is try to jump back into my exploit string. So the way you can do this is, I can show that very quickly to you, but basically in this case, this was an exploit again with an M3U file. So whenever this specific MP3 player tries to open this M3U file, it ends up sort of overwriting the EIP after 4107 bytes. So you would see that I have the specific pointer pointing at this point of time to an instruction which is similar to jump ESP or call ESP. In this case, I'm using push ESP return, and you can see in this case that the string consists of the specified number of bytes. Now, technically, it requires 4107 bytes. I have divided them to try to identify where the value was so that I could put the right EIP pointer correctly. So this is my shellcode, which basically pops up a calculator, and then this is the rest of the part of the string that's required to get to that specific pointer. Once I get to that specific pointer, I had about 9 bytes that I was allowed to use before it got converted and did not allow to exploit any further. So if I only have 9 bytes, there's no way I can basically do uh, an exploit where I can put the shellcode right after the push ESP return. So in this case, what I have to do is actually jump back. So usually there are 3 different kinds of jumps. The two that I want to speak very quickly are far jump and near jumps. The near jump is usually something that is which starts with an opcode EB. Basically, in this case, what you end up doing is jump back 96 bytes. Now again, if I had to jump back 96 bytes, I could have done that. But in that case, what would end up happening is that I would have had to jump a couple of times behind so that I can have enough space left where I can place my shellcode. An easier way would be to jump back by using a far jump. In this case, the far jump that I'm using has an opcode E9. It basically starts with an E9 F4 opcode indicating I'm trying to jump basically 775 bytes behind. and that provides me enough amount of um, space behind so that I can place my shellcode correctly. Usually, what you want to do is that it's going to be hard for you to predict the exact jump back. So you might want to have like a knob sled. So that's what I've done is I've created a small knob sled before my actual payload, and that's where it ends up jumping, and that allows me to control the EIP and then finally execute this calculator payload. So that's pretty much about this. Let's just quickly try to exploit this. So if you look over here to have the MP3 Studio running right now, let's pause at that specific instruction. So let's pause at push ESP return, and then this is the direct jump back M3U, and as you can see that the EIP is pointing to the same address. What I'm going to do is I'm going to execute the instruction step by step so we can watch. And now it has jumped into the knobs, which is this knob sled, which is basically jump ESP instruction. It's executing the knob sled, and this is where it will execute again your jump back. Now observe that I have control of the SE handler. I could have used SEH handler exploit, but this is one of the techniques that you can use rather than using SEH handler, because in that case you would end up having to find basically bypass the software tab that Microsoft installed. So you would have to find pop return instructions from a module that is not safe SEH protected. So to avoid that kind of scenario, or in scenario where you don't have a module that's protected, if you have an exploit like this, you can usually use that. So now in this case I'm jumping back to 001259D1. If you look at this instruction, and once I jump back into the knob payloads, execute the whole, and this is where my calculator payload starts. If I execute it, there you go, the pop-up of the calculator. So let's see that in the fast motion very quickly. I'm going to restart the MP3 player again. And let's do that. And there it is, there's another calculator that popped up. So that's pretty much it. So in cases where you have issues where you have a smaller payload, it's easier to either jump back, have a small jump, or a large jump depending on how large your payload is. So that's pretty much it for this specific section. Thanks.